All right, let's get into this next talk. It's about Linux as well and block device drivers in Rust. My name is Andreas. I work with Samsung in the Ghost team. That's the global open source team. And we have a fancy logo. It's a ghost penguin because Linux and Ghost. And yeah. Yes, I want to thank Alice for giving this excellent first talk. That's a really good segue into this talk that is has a lot of holes where I had the same stuff that Alice had, and she was first in the slides, so I removed that. Thanks, Alice. No, that's great, because then we can go really deep into some other stuff. Now you all heard why we're putting Rust into the kernel, and some of the challenges that we have in that process. And so I'm not going to go over that. I'm going to talk about block devices and what they are and how we can implement drivers for them in Rust. And so hopefully when you leave here, you can all take with you the capability to go home and download this code and write block device drivers in Rust. So it's like a user guide of these patches. And I don't have a lot of slides, so if you have any question during the talk, please feel free to ask them, and then we're not going to have a long, embarrassing silence at the end. All right, so in case you don't know, a block device is a device that can store your data, and it's what you probably are using in all of your laptops and your cell phones to store your data on. We abstract them as a row of blocks of a certain size. They're all of uniform size, and we index these blocks into a linear address space. So it's basically a big array of byte chunks, and we can read and write these byte chunks by sending commands to our device. I hope the text in the figure is visible. Over here? Good. So we send read and write commands to this device. The method of getting our commands to the device may be one of many. It could be like a USB protocol. If you plug in like a USB stick, it could be your SATA connection inside your computer or your NVMe connection, or it could even be a network, something over Ethernet, internet kind of thing, network storage. So we use this abstraction in a lot of places. In Linux, if you've ever worked on a Linux system and maybe you've had to create like a boot media or something, you do that by writing to a special file that represents your block device. You can cat your ISO typically into this file, and it will end up on your USB stick. So these devices appear as device nodes in your /dev directory. And you can, if you are on a Linux system, you can get a lot of information about these the block devices by checking out the sysfs file system. That's like a window into the kernel and what state the kernel has about the block devices on your system. Usually we don't, as end users, access the block devices directly. We often use them through a file system that allows us to have files and directories that are mapped into the block device. Because having like a really long linear address space of just byte blocks is not so useful if you want to store like your PowerPoint slides or something. And this is me trying to draw a picture of the storage stack of Linux. I really hope you can see it looks a little small on my screen, but otherwise I put a circle on my pointer and I'll move around and tell you what is in the figures, in the boxes. Up top here we have our applications, which could be your PowerPoint or whatever application. These usually access the file system through, they access the storage through a file system that is in the Linux kernel. It's part of the virtual file system. That being, we can express a lot of things as file systems, not just storage. And I tried to illustrate that here by having two actual file systems over here that end up in storage. And so also, I can't see you, so if you have a question, you have to speak up. I have a lot of light in the face. Or they can be these, for instance, pseudo file systems that allow us to express other things as files. For instance, the sysfs allows us to express kernel internal state as files. So you can go in and see, there will be like files for each process and files for, I don't know, you can see how many open files are in the system by reading some file in here. And then we have file systems that are stacked on top of other file systems. For instance, we have eCryptFS. That's a file system you put on top of another file system, and it will transparently encrypt or decrypt your files as you open them and close them, read and write them. But if we focus over here, I put in ext4 and btrfs that are file systems that end up storing their data and files on actual storage media of some kind. When you open a file and read or write to one of these files in this file system, the file system will map your file into a certain space in this linear address space of the block device of this long array. And they do that by issuing commands to the bio layer, short for block input output layer. When the commands go here, they are like read this number of blocks starting from this block and this many blocks forward. I looked into the kernel sources to find block device drivers that attach to this particular space in the stack, and I found two. One of them is the device mapper, which you use if you have stuff like full disk encryption. That is also a sort of a recursive thing because you put it on top of another block device. You can also do stuff as, if you have two block devices, you can put them next to each other and have them appear as one big block device. And then there was another one that it took me like a few minutes to figure out what it was, N64. Turns out to be like a Nintendo 64 cartridge driver, because of course there is a Linux port for N64. So, and this particular driver does not need some of the more advanced features that the next layer in the abstraction model provides. And that is the request layer. Because in the request layer, we have mechanisms to queue IOs in per core queues and do scheduling on these queues, like fairness scheduling or quality of service stuff, and manage distribution of IO into different hardware queues. And so I put that down here, the request layer, and underneath that we have stuff like NVMe or SCSI that these drivers may attach to locally attached devices over PCI bus or SCSI host bus adapters, but they actually also can access storage through network. So you can have network attached NVMe devices, for instance. And that ties a little bit into some of the stuff Alice said about the rationale for putting Rust into the Linux kernel, because many people ask me why do you want to put Rust into the storage stack? We don't have a lot of it's not an attack vector. But if you trust your PCI devices in your computer and you don't expect them to trick you and attack you, which we do because we have to, then maybe there's not so much idea of doing this work. But if you imagine instead that you are like Microsoft Azure or Google Cloud Compute or some other kind of cloud service provider, then when you spin up a virtual machine in one of these services, the storage for your virtual machine is actually not locally attached, even though it looks like it. It's attached to the data center infrastructure. So now your storage stack is also network attached, and that comes with a lot of potential attack vectors. So that's one of the reasons to put Rust in this particular area. The next thing I'm going to go into is some of the data structures that the kernel used to manage I/O requests through the stack. The first one is the struct bio, which is the block input-output operation. This structure is, let me see if I can get a cursor here. This is super, it's super, I abbreviated a lot of stuff. So just the stuff that is important for now, I put in these data structures. They are they have a lot of fields. But this structure is basically a vector of memory regions, and depending on whether your operation is a read or a write, it acts as a gather list or a scatter list. So if you're writing data to your device, you'll have the upper layer can say, put all of these buffers into a consecutive range of blocks on your block device. Or if you're reading, read this consecutive range of blocks from your block device and put them into all of these different buffers that I have all around. I give you the pointers here. And these BIOS, they can be chained. You can have like basically it's a linked list, an intrusive linked list. They can point to other requests. Because sometimes if you're talking to a device, it might have a maximum transfer size that it can do in one command, and then we can sort of chop these up, and then we put them in a list so we can complete them all together or issue them all together one by one. And so that's the C stuff that we're trying to represent in Rust. So the bottom layer of the storage stack that I showed on the graph before, the figure before, the request layer handles scheduling and like accounting and all kinds of algorithms that you might want to put into your storage stack. It spins up a per core software queue that it will put your requests into, such that you can have thread local data storage all the way through the storage stack. Like imagine if you just had one queue and all cores issuing I/O to your maybe single NVMe disk in your laptop, they would have to take a lock or use some kind of lock-free queue every time they put stuff on the I/O queue. But now people figured out that as we got more cores, it's probably a good idea to have like per core queues. So that happens in this layer. And then we do all of our scheduling and rearranging. For instance, if we have old disk drives, we also apply algorithms where we look for IOs that are next to each other, and we move them next to each other and issue them in order, because rotating disks, the arm on the rotating disk actually takes some time to move between tracks and locations on the disks. So we want to do as much I/O as possible when the arm is over a given track. So all of that stuff can be done there. When we're done with that, we hand the I/O off to the hardware queues that are managed by the device drivers. And like modern disks, they have at least modern NVMe devices. They typically have multiple queues that they can store in host memory or in device memory, and they might not have as many as you have CPU cores. So that's why I have like an M to N relationship here. So we might have to move multiple CPU queues into fewer hardware queues here. But so depending on what kind of drive you have, if it's like an enterprise-grade drive for a super many-core computer, it'll probably have many hardware queues. For your laptop, maybe it has 4 or 16 or something. And this point here is what the Rust abstractions that I am working on are covering. So they allow you to hook into this point and say, I'm a block device, and fill in some methods, and then your block device will appear in all of this layer upon layer upon layer stack of stuff. The bio I showed before, when we place it into these request layer queues, we wrap it in another structure called the struct request. Very fitting. And the most important thing about this is it points to your gather-scatter list, the bio, and it has a place to put a tag. And the tag is smart because when we issue I/O to a device via some kind of protocol over some kind of transport, that could be PCI or network or USB or whatever, we are not issuing one at a time, because then we would spend a lot of time waiting while the I/O is getting processed in the other server, if we're talking networked file systems, or in your drive, or while we're waiting for your platter to be in the right position so we can do a read. So we pipeline all of these requests. We fire off a lot of them in some kind of queue, and then at some point the device will come back and tell you, now I'm done with this request. And it might not come back in order. The devices can do all kinds of scheduling and optimizations internally. So your stuff is going to arrive back in your completion queue out of order, potentially. And therefore, it's really good to have something to identify your request when it comes back, so you can go and fetch the request that matches the completion and tell the kernel up in the stack, now this particular I/O is done and the data is in the place you asked it to be. And to that effect, we have the tag. And we have a data structure in C in the kernel called a tag set that has a very efficient way of mapping integers to pointers and the other way around. And when I mean it's really, really super efficient. Some people spend a large part of their lives making this really fast, because then stuff like cat videos on Instagram or whatever appear faster. And that is something we all want. Yeah, so taking this architecture into account, the C components that the Rust abstractions are going to wrap are these I put here. We have something called a gen disk. It's short for generic disk, and there is one of these structures backing every block device in Linux. The gen disk has a tag set, which is the very efficient mapping structure. This tag set also has a vtable. A vtable is a table of function pointers that the driver implementation provides to the kernel, and then the kernel calls into this table to do stuff such as enqueue requests with the driver. It's sort of like an polymorphism kind of thing from C++, but instead of inheriting from something, we just fill out a struct full of function pointers and hand it off to the kernel and say, now I'm a block device. And then we have the struct bio and the struct request that we talked about before. In Rust, we have a set of almost, I think they are one-to-one mappings to Rust types. We have this gen disk, the bio, the request, the tag set, and then we have this operations type, which is actually a trait that you implement. And this trait has a number of required methods, and these would be like a queue IO, the kernel calls that. So they are callbacks that your driver will get. So you implement that, and then you're a block device. And we will have an example of that. Now we have code. So here we have stuff needed for setting up. We have a tag set that you build with a try new method. Alice talked about why fallible constructors are important. If we are out of memory or something else, we don't want to just crash or panic, we want to report an error up. And we have the gen disk, which we pass the tag set. And you remember the tag set is the translation between tags that we send to the driver and the requests that the kernel owns. And one thing to note here is that this tag set constructor actually returns an initializer, which is what Alice talked about with the initialization. In some cases, we don't want to split allocation and initialization because it's potentially unsafe to have these C data structures in an uninitialized state. So it's actually not returning an instance. It's returning a function that you can call to create an instance. And to create a block device, you basically just need these like 4 lines or something. You create your tag set, and then you have your own struct implementing the operations. That's what the tag set is generic over. And you create this gen disk and pass it the tag set right here. You might want to set a name, and then you call disk.add, and then you're good. Then your custom home-brewn block device will appear in /dev. And also, there's one more thing that you absolutely need to do for it to be fun, and that's to set a capacity as well, because otherwise, I just tried this, and then it shows up with like size 0, and it's not much fun. But of course, you still need to implement your driver, and for that, you implement the operations trait on a structure that you provide. And this trait has a number of associated types that are data that you can associate with these other structures that we talked about before. Many of the kernel structures have a void pointer that users of the structure can use to yeah, someone is laughing because, of course, void pointer is a source of type confusion bugs. And not in the Rust. In Rust world, they are typed. So we have these data types that we can associate with these different structures. And in this case, I only put something on the request. So this data for the request is actually stored right next to the request structure. So basically, if you have a pointer to a request, what they do in C is they say, what is the size of a struct request? And then they just move the pointer to the bottom. And then they say, whatever place you're pointing to out here now, it's actually a whatever protocol specific thing that is stored here. But in Rust, we managed to make it such that it is typed. And you don't need to implement all of these, but they can come in handy. So I put just unit for most of them in this example. And you need to implement like 4 methods for it to be for the driver to actually probe. But most of them can be empty. But you definitely want the queue request, which is the callback you're getting when the driver is enqueuing something with your, when the kernel is enqueuing something with your driver. And now we are going to see it in action. I hope, maybe, because we all know that you need to sacrifice to the demo gods for this to work. Let's see. We're going to see the Linux screen of death. So, to actually show you that, to encourage you all to go home and download these patches and build your own block device driver, I will show you how little code is needed. So, let me just give some context of where I am. I cloned the Linux source code into a folder called Linux, and then inside drivers block, I put a file called myblock.rs. And the only thing I need to do to have it compiled by the kernel is, of course, there's like a little bit of stuff you need to do to have Rust enabled in the kernel, but there's many excellent guides on that. You need like the right, now,
You need a Rust file.
yeah, and you also need network connection to present to this monitor. It disappeared. We are back. Okay. So you put your myblock.rs or whatever you want to call it. You add it to the makefile, like so. Just put like object-y and put the name of your file and then .o. Then make will pick it up and build it into the kernel. So it will be not a module. It won't be loaded. It will just be like part of the kernel. And then you import a bunch of stuff from the kernel crate, which is like contains all of the abstractions for all of the subsystems that we support. And then you put this module macro where you put in a name of a struct that will be your driver. And then this in this struct you implement kernel module, and that thing will have like I don't know if it can have more. At least it will have the init function. That's called when the kernel initializes your module. And here you see I have the code from the slide before. More or less, we create a new tag set. We create a disk, and then we put a name for the disk. We set a capacity, and we add it. And then you can't let go of the disk because then it will be deallocated and the destructor will remove it again. So technically it will have worked, but you won't see it. So I just hold on to it and put it in here, and then it's not used for anything other than keeping it alive. You could also like box leak it, but then you could never tear down again. So that's it. And then you implement this operations for your module. And I didn't want any request data, so I just did nothing. And at least you should, so you have this queue function that will get past this request that will be will contain a pointer to this block IO scatter gather list, and so you can do what is meaningful with that to complete your request. I just started and tell the kernel the request went fine. So it's okay to lie when you're just playing around. And the rest of the methods just have to be there. You don't have to do anything in it. And now you can compile this, hopefully. Let's see. Are
you doing screen diving?
No. Oh, maybe I can like use a hotspot or something. Okay, I'm terribly sorry. That is unfortunately out of my hands. Okay, and then we put the file, we edit it to the makefile, and we're going to build it. I have a shortcut for that, short for just Linux. Just is a really cool command dispatcher written in Rust. If you haven't tried it, I suggest that you do. And let's see. If I can, you see it built our source. It complained about I didn't document my crate, which is you should always document your crates.
Sorry, I got a question.
Yeah.
You say that just does the tool advertise like an alternative to make?
No, it's like if you run complex build commands all the time. What I used to do is like I would make a bash script and put all of my stuff in there, but bash doesn't have like one way of doing stuff like this. Sometimes I would use Python as well. Just is like just a command dispatcher. It doesn't do anything else, and it sort of forces a certain style. So if you're like a messy person like me, it's cool because it sort of restricts what you can do. And actually I can just show you. It has a just file because now I did a lot of stuff anyways, but anyways, this is a Linux target.
That's not like some kind of alternative to make?
Yeah, because make does like a double pass and does like all of this dependency resolution stuff. This is just one thing, and you have like a target, in this case L, and then it will do whatever is in this target. In here I put a piece, like if the first line is a shebang, then it will pass it to so you can have a script, and there's command substitution with like a double handlebars kind of thing. So you can see here what it does. If you're moving between kernels a lot, you might need a certain version of bindgen or a certain version of the Rust compiler, as Alice said, and this just handles that, makes it easier. Let's see if I can. I hope I'm still. And of course, now I build it, but we also need to run it. And I go just run, and what this does, it boots the kernel we just built in a QEMU virtual box. No, it's not a virtual box, a QEMU virtual machine that runs a Debian userland. And now I have like an SSH connection into a virtual machine running the kernel we just built with a Debian userland, which is nice because now we can go ls blk, and we can see we have a MyBlock block device of 2 megabytes. And of course we can see it is in MyBlock. It's there. There's a file that represents our device, and we can also talk to it. We can maybe do something like this. Always do that. So what this does, if you ever do work with block devices, this is a really neat program. It's called the Flexible I/O Tester. It will just read and write from your block device and like tell you how it went. Now you can see it's writing 100 megabytes a second, and it's reading similar, and we don't have to stand and stare on that. When you stop, it tells you like how fast it went. We can also ask it to maybe verify how it went. Let's go for, let's see if we can, if I can remember. It's called like, what is it? It's because my, sorry. So the last parameter is like a do verify. And if you remember, we just completed the request. We didn't actually store any data. So now when I run this with the do verify, it's a...
No, the screen sharing back.
So anyway, what I tried to do and show you was like, if I put this I/O tester to actually read back and verify what it wrote, it tells me I'm full of nothing. Yeah, that's basically it for the demo. Let's see if I can go back as well to the presentation. Where did that go? Here.
Why is it so slow? 150 megabytes for doing nothing.
Maybe, I don't know, it's compiling in like debug mode with all of the debug symbols, and I don't know. It's running a VM, but it's KVM accelerated, so it's like sort of should be fast. It's not accessing hardware, so it should be okay. Anyways, we have 2 drivers that use these abstractions. One of them is an NVMe driver that is it's sort of it's full of unsafe code and a work in progress, but it works. So you can actually boot your laptop with it and run Linux on your NVMe device with this Rust driver. I wouldn't recommend it if you have like anything because it didn't have enough testing for that. And then there is a null block driver that is a piece of testing infrastructure similar to what we just implemented. It has a ton of different options, and then you can try out the storage stack under different conditions. And you can set it up to like throw away your requests, or you can actually also memory back the device, so it becomes like a RAM block device kind of thing. And then you can put like file systems on top of that if you want, and have like fast disk to test stuff, right? And this code that I have on the screen here is from this null block driver, just to show you what it would take to actually store the request and service them properly. And if you recall, our request has a pointer to this bio. That's basically a getter-scatter list. What we can do is we can use the iterator trait to iterate over all of these pages of memory. A page is the smallest amount that we can handle in our virtual memory. Doesn't matter too much. It's usually 4 kilobytes, and that's the unit we're operating with. So we can map all of these, and then for each of these we call a transfer method, and we pass in a tree, which is actually Alice talked about the X-array. It's like it's a mapping structure that maps pointers to data. And depending on whether we have a read or a write command, we do something with it. We call read or write. The rest of the stuff we just throw away because we don't care. And for the read operation, we can go and ask our tree for this. I said pointers, that was a lie. It's an integer. So it uses the, you remember our block device is a linear address space of blocks. So it uses this block number to index into this tree and ask, do you have any data for that? If there is, we can write it back by using a copy from the page, and then it's copied into the buffer from this tree. Or if on writes, we can ask our tree, do you have anything for this index? If yes, then we just get it. Otherwise, we can insert it. We don't have any locking issues here because at this point in time, we already have a lock for this tree. And so let's hope that the allocation of this new page doesn't sleep. And then like copy it the other way. And if we do that, we get something we can actually compare to the C version of the null block driver that also is able to store data in random access memory. And this plot is a comparison between the C version of the null block driver and the Rust version. And what we have up here in the first row of plots is random read workloads. In the bottom row of plots, it's random write workloads. Each column of plots is a different queue depth. So you remember we had the tags that transfer between a request and a tag. This can have a limited range that sets the maximum depth of requests you can queue with the driver. So here we vary that from 1 to 128. And then the 3 colors are 1, 2, and 6 worker user space threads issuing IO. And the last one is block size. So the size of the IO request. That's what you have on these lines out here. And the graphs show the relative difference from the C version to the Rust version. So positive, Rust is faster. Negative, Rust is slower. And if you look closely, you will see that the difference is less than 5% over all of them. And in general, Rust may be a little slower, but it's like if you sum all of it up, it's pretty close to being 0. And these are also like the average of 30 runs, where the average is modeled with a t-distribution, and then there is like the bars are 95% confident intervals. So there's not a lot of noise in these measurements, so they should be sort of fine. Yeah. And the bottom line is we can use Rust here. It's fast enough. That's what I wanted to say with this figure. Yeah. And that was my last slide. The code is available. You can go to the rustforlinux.com, and there is a pointer. I invite you all to take it and play with it. There's many this null block driver and the abstractions that support it, I hope to get them into the mainline Linux in the first half of 2024. I think that it's possible, but let's see. There is also the NVMe driver. First of all, it needs a lot of work, and second of all, there's not a lot of support for getting it into the tree from the upstream community. But I still keep it alive and keep it functional on top of latest Linux release. As I said, it needs a lot of work. So if anyone is into that kind of stuff, there's plenty of unsafe blocks that needs to be removed and have proper abstractions, proper comments. Yeah, you're very welcome, and contributions are accepted. Mm-hmm. I can only see you, so if anyone has, maybe we can turn on the lights or someone can moderate or something.
Meanwhile, can you explain those nice bit shifts around sector?
Yes.
Remember to repeat the question.
Sorry, so I was asked about if I could explain why I shift by 9 here.
And then by 3 a little later.
Yeah, so I had a no, it's a difference in powers of 2 between probably blocks and sector size and page size, something like that, maybe.
That's officially NSA approved answer.
It's the sector shift, so it's like even though the sector size of the devices can be like 4K or 512 bytes or something else, the sector size in the Linux kernel is, for historical reasons, I think 512 bytes. And so for a page is usually, there's a constant called the page size. So the IOs for this driver is probably page size. And so to get them into the right index, you shift the sector that Linux uses, 512, up into the find the page index. Yeah, I had a comment say like a /to-do. Please use a constant instead and like fix this ugly stuff. And then I thought it didn't look so nice on the slide, so just no one's gonna notice. Yeah.
Yeah, so I mean, like from Alice's, right, the performance was basically the same from Linux Rust. Is like the performance difference here, is that because it's a different algorithm the Rust is using?
No, I'm not sure why the difference is there. I looked quite a bit into it. What this driver does is super simple. It just loops this scatter list and writes the content into memory or reads from memory into this list. And the C driver does exactly the same. And the generated code even use the same memcopy function underneath. So I think maybe it's related to how I implemented the iterator trait for the for the list. It could be like, I don't know, it would be nice if it was like just slower or just faster, but in some cases it's faster, in some cases it's slower. So I think it's just like code gen and like randomness in the code gen more than anything else. Mm-hmm. Mm-hmm. Yeah.
Yeah, the block device we created was 2 megabytes, right?
Yes.
You wrote that you created it with capacity 4096.
Yeah, so that is so the question was, why did the block device show up with the size 2 megabyte when the capacity was set to 496? 4096, and I think so. If you shift 4096 block size bits up, you get 2 megabytes. Well, it's because of the unit is not bytes; it's sectors, and sectors are 512 bytes. So multiply by 512, probably you get 2 megabytes. Yeah.
So 4096 sectors.
Yeah. Should be 2 megabytes. I do believe that
This is all in documentation, right?
that's what I was about to. Let's see. Actually, let's just go and check. So I put it right here. Maybe let's see if did not work. Set, was it like capacity? It does not say the unit, unfortunately. Okay, which is like, oh, does it do? Call the, oh yeah, it says second, but I should have like to do. Put it. Absolutely, I would take that. Yeah. Yeah.
Maybe one more?
Mm-hmm. Yeah, is anyone, yeah, Emil, go.
You have an example in code where you pulled in stuff from the kernel. One of them was called, it was a trait called ForeignOwnable. Can you talk about that?
So the question was, there was a trait called ForeignOwnable, and what is that? So that is a trait that allows us to convert a Rust object to a void pointer, so we can pass it to C and store it in these private data fields. We have like a private data void pointer or something, so we can take our box or an arc or something else, turn it into a void pointer, and when we get it back, we can convert it back in a safe manner. So by requiring that the data type implements ForeignOwnable, we know that it's something we can safely store in C side in a void pointer. Yeah.
I know I said last question, but Troels won the secret raffle to actually get to ask the last questions.
Sure. Alice had a chart of like unsafe versus safe. Like how big is the distribution? Do you have the same like?
I do not have a chart, but for the null block driver, it's super simple because there's no unsafe code in it at all. All of the unsafe is in the abstractions, and there is a lot of it in there. But I'm working on getting it very well documented and very well explained why each unsafe section is safe, which is actually challenging. And also the null block driver, the implemented features is not that many. So it's like maybe, I don't know, 200, 300 lines of code. So it's not that much.